faithfully conveying value and interpreting great books from around the world. Hello, this is Sally's Book Talk. Today, we're exploring the book, The Wonderful World of the Periodic Table. When you hear periodic table, you might picture a huge, complex chart filled with letters. It may seem distant, but the author shows us how the periodic table exists in our daily lives. Why does eating too much salt cause high blood pressure? Why are gold and silver chosen for jewelry? How do neon lights produce their glow? All these questions connect back to the periodic table. The author is Japanese science writer Ryoka Yoshida, who studied quantum chemistry at the University of Tokyo as an undergraduate. Though passionate about his field, Yoshida wanted to work in life-related areas. So, after graduation, he pursued a doctorate in medicine and earned his medical license. While practicing medicine, Yoshida also hosted TV programs and served as visiting professor at Tokyo University of Science. His solid academic background gives him deep insight into the periodic table's importance. Yoshida combines elements, real life applications, to present a chemical worldview without equations, helping you understand elements' relationship to the human body and showcasing chemistry's charm. Complex chemistry transforms from dry equations to the elemental magic that creates our beautiful world. Perhaps, as the author says, we missed the periodic table's magic in high school because teachers never showed us how useful it truly is. The author wrote this book to help readers discover science's joy. I'll explore three key aspects to help you grasp the elemental world's grandeur. First, what patterns exist in the periodic table? Second, how are elements connected to the human body? Third, what roles do rare elements play? First, let's examine what patterns exist in the periodic table. Before exploring the periodic table, let's briefly cover what elements are. All natural matter consists of atoms, which contain a nucleus and orbiting electrons. The nucleus holds protons, positive charge, and neutrons, neutral, while electrons carry negative charge. The proton count is called the atomic number. Atoms with the same number of protons in their nucleus are collectively called a chemical element. For example, atoms with 6 protons are called carbon, and its atomic number is 6. In 1869, Russian scientist Dmitry Mendeleev discovered that element properties exhibit periodic patterns. Based on these patterns, he organized known elements into a table, creating the periodic table. Initially incomplete, Mendeleev left gaps for undiscovered elements, predicted their properties, and gave them temporary names. As French chemist Paul-Émile Lecoq-Goybos-Baldrin discovered gallium and German chemist Clemens Winkler discovered germanium, these gaps were gradually filled. The properties of these new elements matched Mendeleev's predictions, confirming the periodic table's scientific validity. The periodic table quickly became chemistry's focal point, marking a milestone in the field. Currently, 118 discovered elements are arranged by increasing atomic number in 18 columns, groups, and rows. For example, hydrogen with the smallest atomic number occupies the first row and first column. If you still can't recall the periodic table's appearance, that's perfectly fine. Well, we'll provide the periodic table in show notes. Seemingly chaotic, yet fundamentally ordered. As mentioned earlier, all elements consist of atoms containing a nucleus and orbiting electrons. The number of electrons in the outermost shell determines an element's fundamental properties. Elements in the same column typically share outer electron counts and similar properties, like potassium and cesium in column 1. Both easily lose their single outer electron to form 1s cations, readily combine with anions, dissolve in water. The human body contains significant potassium. Due to their similarity, cesium entering the body travels through potassium channels where it's mistaken for potassium and absorbed. In 2013, operational errors at Japan's Fukushima nuclear plant caused massive leaks of highly contaminated water containing radioactive cesium. Once this radioactive element enters the body, it releases ionizing radiation that dramatically increases genetic mutation risks, ultimately causing higher rates of stomach, lung, colorectal cancers, and leukemia in Fukushima. Similarly, copper, silver, and gold share the same periodic table column with similar electron configurations, making them stable and resistant to reactions with air or moisture under normal conditions. That's why they're chosen for decorations and jewelry. Chemical elements permeate our lives and bodies. So, how are elements connected to the human body? In part two, you'll discover the elemental composition of the human body and how elements drive life processes. First, let's explore where elements originate. Actually, most natural elements come from space, very few formed on Earth itself, because element creation requires temperatures exceeding 10 million degrees Celsius, while Earth's hottest core only reaches 4,000 to 6,800 degrees Celsius. Clearly, Earth lacks such extreme heat. In the vast universe, ultra-high temperatures mainly occur in three scenarios. First, after the Big Bang. Second, nuclear fusion inside stars like our sun. Third, when stars die during supernova explosions. Natural elements are forged precisely in these three cosmic events. 4.6 billion years ago, rocks and dust orbiting the sun coalesced into Earth. Throughout the vast eons since, Earth's elemental composition has remained nearly unchanged. What changed wasn't the elements themselves, but their combinations. Meaning, Earth's life is built on countless chemical reactions, linking our body's elements directly to cosmic origins. Over 99.5% of human body elements are hydrogen, oxygen, carbon, and nitrogen. Hydrogen and oxygen dominate since our bodies are mostly water, H2O, naturally elevating their proportions. Carbon ranks third due to its abundance in carbs, fats, and proteins, while nitrogen places fourth from its high protein content. Beyond these four, the remainder includes phosphorus, calcium, sulfur, sodium, potassium, chlorine, magnesium, and other trace elements. Looking at the periodic table, human body elements cluster near the top, elements with smaller atomic numbers. The body also contains trace elements like iron, zinc, manganese, copper, tin, and iodine. But elements beyond the sixth period are virtually absent. Why do we find so many top period elements but hardly any from the bottom? The answer is simple. Top period elements abound in the cosmos, while bottom period elements are far scarcer. During 3.8 billion years of evolution, life continuously tested chemical reactions, adopting those compatible with the environment to survive. Otherwise, natural selection would eliminate them. Thus, human elements primarily consist of cosmically abundant ones. So, among these elements, which drive life's activities? Body movement relies on muscle tissue, while thought depends on the nervous system. At first glance, these seem unrelated. Yet, muscle contraction and nerve conduction share nearly identical mechanisms, both requiring sodium and potassium. How exactly do sodium and potassium influence muscle and nerve function? Both exist in the body as +1 cations. Sodium ions concentrate outside cells in lymph and blood. Potassium ions concentrate inside cells with dedicated membrane channels for both. At rest, cells maintain negative internal charge and positive external charge. When muscle cells receive stimulus, say, a pinprick to your finger, sodium ions flood inward, reversing the charge and triggering contraction proteins to withdraw the finger. Nerves work similarly. Charge reversal stimulates neurons to fire impulses, signaling the brain about the painful prick. Then potassium flows out, restoring the charge balance. This reset prepares both muscle and nerve cells for the next stimulus. You might wonder, after this cycle, sodium increases inside while potassium decreases. How is the original state restored? That's when the sodium-potassium pump kicks in, also called the sodium-potassium transporter. It pumps those moving sodium and potassium ions back to their original positions. In short, the constant movement of sodium and potassium ensures proper muscle and nerve function. From this explanation, you can appreciate how crucial sodium and potassium are. A deficiency in either element causes health problems. Sodium deficiency leads to dizziness, fatigue, and loss of appetite. Potassium deficiency causes muscle and nerve dysfunction, weakness, and irregular heartbeat. But excess elements are also harmful, like how limiting salt intake is now common health knowledge. Salt is sodium chloride, crystals formed by sodium and chloride ions bonding. Excess chloride isn't problematic as it's excreted through urine. It's sodium we must avoid over-consuming. But why does excess sodium cause high blood pressure? Our blood and lymph have sodium concentration limits. When overloaded, the body retains water to dilute sodium, increasing blood volume that presses outward on vessels, raising blood pressure, and causing swelling from excess lymph fluid. Many mistakenly believe eating extra salt is fine if they drink more water to flush out sodium. They don't realize is our daily sodium excretion through urine has a limit. When intake exceeds this limit, the body can't eliminate excess sodium, gradually leading to hypertension. Meanwhile, we mustn't neglect potassium intake. Fruits and vegetables contain potassium, especially kelp, and a balanced diet provides enough without supplements. Excess potassium in blood or lymph makes it hard for potassium to exit cells, disrupting muscle and nerve function. Too much potassium also affects heart rhythm and can be fatal in severe cases. So, potassium intake must be controlled too, especially for those with kidney issues who struggle to excrete it. These are all familiar elements we've discussed, but there are seemingly uncommon elements in daily life that you actually can't live without. Part 3 explores the roles of rare elements. I'll discuss rare elements from two perspectives: rare earth elements, representing horizontal balance, and noble gases showing vertical similarity. First, let's examine rare earth elements, gaining recent attention. From Tesla's electric vehicles to medical MRI technology, we owe much to rare earth elements. What exactly are rare earth elements? To answer this, we must distinguish rare earth elements from rare metals. Rare metals have scarce surface deposits or difficult extraction processes, like titanium, vanadium, chromium, manganese, nickel, etc. The rare earth elements specifically refer to rare metals in Group 3, periods 4 through 6 of the periodic table. That sounds complex, but simply remember, rare earth elements are a subset of rare metals. They're called rare earth because they're sparsely distributed in soil. You might rarely encounter them daily, but their impact is enormous. Magnets made from rare earth elements are rare earth supermagnets, prized for maintaining powerful magnetism long term. Many cutting-edge technologies rely on these strong magnets: LED lights, TVs, fluorescent screens, fuel cells, car exhaust purifiers, and more. For example, in medical imaging, doctors previously relied mainly on CT, computed tomography scans. Now, radiation-free MRI is standard. CT is cheaper, but uses X-rays, gamma rays with radiation exposure, and only produces cross-sectional images. MRI technology places the body in a special magnetic field, displaying cross-sections from any angle. Even tiny tumors can't hide because MRI's high-performance magnet creates exceptional signal-to-noise ratios. This means strong signals with minimal noise, enabling superior imaging quality for faster, more accurate diagnoses. Beyond medicine, strong magnets power electric vehicles, maglev trains, and hybrid or electric car engines, which are magnet-driven. Stronger magnets mean greater vehicle power and higher speeds. Without rare earth elements, Tesla would only exist in sci-fi movies. Rare earths have unique properties: extremely high melting points and excellent thermal conductivity, preventing heat buildup during operation while ensuring part stability, making them invaluable across industries. Recently, as rare earth value became apparent, global powers joined fierce competition for them, putting rare earth in frequent headlines. Similar electron configurations and chemical properties among rare earth elements lead to highly concentrated mining locations. Most global rare earth deposits are in China. These elements perfectly demonstrate the periodic table's horizontal consistency. Meanwhile, Group 18 noble gases represent the periodic table's vertical similarity. Now let's explore vertically similar noble gases. They occupy the rightmost column. You'll recall immediately, yep, helium, neon, argon, krypton, xenon, radon. Their fully occupied outer electron shells create remarkably consistent properties. Noble gases exist as individual atoms. Why is that? Because filled electron shells prevent reactions with other atoms even among themselves. Hence, they're called inert gases, inert meaning chemically lazy. Now, let's examine common noble gas applications. You're most familiar with helium, the universe's second lightest gas, just slightly heavier than hydrogen. Helium's resistance to chemical reactions makes it non-explosive. Thus, it's widely used in airships and balloons. Below helium comes neon. You might not recognize neon, but it's actually all around you. Restaurant signs and colorful neon lights contain neon gas. An electrified, intense energy pushes electrons from stable orbits to outer shells. This unstable state makes electrons desperately return to original orbits. Excess energy releases as light during this process. That's how neon lights work. After neon comes argon, second most abundant atmospheric gas after nitrogen and oxygen. It's easily extracted and low cost, giving it wide applications. Filling argon into incandescent bulbs prevents the filament from oxidizing in air, extending its lifespan. Argon can also treat hay fever. When turned into a special plasma and sprayed on nasal mucosa, it blocks contact with pollen. This utilizes the trait of inert gases being chemically unreactive. Finally, let's discuss xenon, positioned later in the periodic table. It's rare in the atmosphere, expensive, and used only in very specific applications. In 2003, Japan launched the Hayabusa spacecraft, which brought back samples from asteroid Itokawa to Earth. The propellant used in Hayabusa's engine to return to Earth included xenon. In the vacuum of space, the only way to move is by expelling mass at high speed using reaction force. Only gases can be expelled rapidly, and xenon fits perfectly. It's a gas and very heavy, making it ideal as a propellant. With this, we've completed our interpretation of the periodic table. Chemical elements form the foundation of our material world. Exploring chemical elements helps us understand the laws governing all things and discover the wonders of the universe and life. When encountering an unfamiliar element, we can find its position in the periodic table to learn its properties and uncover nature's wisdom. All right, that concludes our journey into the wonderful periodic table. Study notes are below the audio. See you tomorrow.